So today we're going to speak about supporting query intention in Fusion 4.2.
Hi everyone, my name is Atousa. I'm working on the search platform at Uber, and my main research, the focus is service search and discovery, also data mining and information retrieval.
Hi, and I'm Stan. I've been working in the industry for 21 years, working for companies like Microsoft, Gap, Visa, and currently Uber. Yep. So a little bit of background. So Uber has a culture of building things from the ground up. So as part of basically the evaluation of building a enterprise search application or platform for Uber, we basically evaluated the build versus buy decision. And basically, we partnered with Lucidworks in order to build our solution. We evaluated basically the criteria for actually building it ourselves versus actually purchasing an off-the-shelf product. And based on the Lucidworks use of open source components, as well as the partnership that we have with the engineering organization there, we decided to basically go with Lucidworks to actually build the actual search platform for Uber.
My phone here, then I can change. So Uber tries his search engine with corporate information from employee directory to NGDoc on legal documents or Jira or Fabricator. So we need to support the complicated ingestion and indexing this document. What we build is not only like a simple site search. We built a general search platform. And the problem with building a general search platform is that when a user, we have a little context when a user search on our platform looking for the content. So in order that we can improve the relevancy and return a better result, so what we have done is that we use the Fusion capability to initially build custom rules. And this custom rules is basically boosting certain document based on the top case search result on our platform. But the problem, like here is an example of the query pipeline that we have and we build. As you can see, like all of this kind of the rule-based and static. And as we implemented this pipeline, we find out that there is lots of issues. First of all, we were not able to, we need to have like a domain knowledge to understand the ranking criterion, and it is very time consuming. And also after we implemented the rules, we find that they are very high maintenance because let's say we have the concept drift or covariate change, or we have some changes in the document content, we have to go and revisit the rules frequently. And also, we were not able to generalize the rules across the data sources. So because it's very these rules are very domain specific. So after we started to generalize them, we obtained contradictory ranking weight for data sources. And it leads to adoption of the machine learning approach into the search platform. And we started like using the Fusion capability to maintain the rule-based mechanism that we already implemented, and also add like the machine learning option that we have in Fusion. And basically, as we are expanding, we have to support more documents. And in order that we can support more documents, we need to have a better understanding of the query. So we thought that probably we have to switch to the query tagging and use the machine learning to generalize the tools.
Great. So speed matters in basically delivering more models rapidly and iterating through to basically test the various different models that we wanted to use in order to basically deliver on specific features on the platform itself. So basically, we in the software development world, basically DevOps enables the transformation of the software delivery lifecycle to enable software engineers to basically own the complete lifecycle of the application from development all the way to production. So basically, instead of throwing software across the wall, they basically enable developers to understand how the actual applications actually behave in production and allow them to better accelerate the actual speed of the delivery of software to those environments. So in the world of machine learning, we basically depend heavily on MLOps, basically, to accelerate the actual delivery of models to a production environment. Therefore, basically enabling rapid iteration of the models and then allowing the complexity of training, testing, and deploying the models to bring that basically cycle down to from months to weeks or even hours. One aspect of that is we enabled the ability for anyone who has no or limited knowledge of programming, data scientists, analysts, and non-developers to release this code through a simple predict function that allows them to wrap their models. As long as they basically can write a simple predict function, they can actually release this code to production. And the actual integration of this through the Fusion platform is through a set of stages in the query index and query pipelines that allows you to integrate an external actual model service into the actual Fusion platform itself. So here's a diagram of the actual process of going through Fusion to the actual ML pipeline itself. If you could actually see that, the actual ingestion of actual documents goes through the REST API through Fusion to an index pipeline that has an index stage to an external ML service. That external ML service goes through the process of basically ingesting the actual data and analyzing it and transforming it to extract the features associated with that and passing the actual data into training the model and actually validating it and actually productionalizing the actual model into a service that can be called from the query pipeline stage. So external applications can call that model through the query stage to the actual model serving service.
So here is a typical machine learning pipeline, and we're gonna, for the purpose of the query tagging, we only cover the feature extract pipeline and model training and model deployment. So for the data ingestion, we mainly, and this is the whole overall stage that we have. So what we do is that we do some kind of the feature extraction online and offline. So on the signal collection, for example, and data sources that we already index them and store them in the Solar Fusion, We get this information offline, gather the features, and extract the feature. And then we use this, store them in a repository, and then we use them for the model training. And also we do this online by getting the query information and then do the feature extraction. So on the ingestion side, we are not doing something like offline extraction, online extraction. So it is like a typical data ingestion and indexing. So we have like an independent service to gather the information, index and ingest, and they run on a schedule. But therefore, in order to do feature extraction offline, we are using a toolbox that has been implemented at Uber and called Ludwig, is an open source. Ludwig helps us to do the static feature extraction, and we save all the features on the repository.
Right. So basically, Ludwig is a toolbox created by our conversational AI team that enables anyone to basically build models using TensorFlow. It allows you to basically train the models and also test the deep learning models without actually writing code. So here is basically the Ludwig model is basically a concept around having input features as data types, as well as output decoders as data types as well. So from this perspective, we have various different data types that represent specific models that would be implemented through the encoders and decoders. For the deep neural networks. So for example, if we take a text feature data type as an encoder and a category feature as a decoder, we're basically creating a text classifier application with that model. And here's another example of basically taking an image feature data type and then as the encoder, and then taking a text feature as the decoder. And that basically allows you to create a image annotation, a classifier service for your model. Here is an example of a configuration for the Ludwig, for the actual Ludwig training. The input basically describes the actual decoder, or sorry, encoder type, as well as the deep learning model that is actually associated with that. And the combiner basically takes the interconnected layers to basically combine the actual results of the various different encoders, and then from the output features, it basically maps to a specific data type for the decoder layer. The training section near the bottom, I don't think you could see that. It provides various different parameters associated with training the models. And the pre-processing step basically allows additional pre-processing steps, including the split for the actual training, validation, and test sets provided into the model. The actual input for the data set is a CSV file that basically has columns for the various different features. It's just a matter of running the Ludwig experiment tool or flag to actually enable training of the model through using the CSV and the definition file. And then the predict task is basically allowed to load the actual model, and the server task is used to actually create a fast API service associated with that model to serve as part of your model in production.
So after training a model by Ludwig, actually we wrote a very simple code to train this model. And this is you can evaluate a model very easily. You can visualize it very easily using Ludwig. And so this is what just I want to show that the result that we had and what we had, it's easy to use and set the hyperparameter, very easy to use the algorithm that you need. And then here we have been doing the cross-validation. And this is the result from the cross-validation. And by visualization, it's very easy to tweak the hyperparameters to evaluate the different models. So here you can see the accuracy score or logarithmic loss in this example. So back to the feature extraction, we mentioned that we do online extraction as well. And the reason is that when it comes to the query tagging, pre-calculated results and offline approaches are not sufficient. So we need to extract a feature from query and do some extraction online. So in order to do the online, we just do like the model training using code. So we have a service called feature logic. So we implemented all the business logic over there. And this business logic has been implemented. And we get the query and the feature logic service, by getting the query, extract all the features online and store them in the repository. So this is I'm explaining here that in order that we understand better the query, we map each query segment to the intended corpus attributes. So you can see some example of the query in here. So we search the token first on the index document. So, and after, by getting the position of the index document and query token, we can map it to the field, the specific field. For example, there is a query in here. You see each of these query mapped to the specific field, a specific data source, and also a specific field. So now we don't need to do boosting, like do the boosting statically. So we can interpret this parameter to the Solr query and then do boosting like the dynamic boosting. So we expand the query and do dynamic boosting based on this mapping. And then finally, at the end, the model is like kind of the softmax classifier. And then it just returns a probability value. And this probability value shows that gives the probability of the query being in a particular data sources. So according to this information and probability, we can do dynamic boosting.
Great. So a little bit of just highlights around what we're actually planning for the future. So we're looking into conversational predictions, so more accurate predictions and deeper natural language inference. The search interface will be more like talking to a real person. Model personalization, so stacking models to enable personalized representative semantics. So deep hierarchical ensemble modeling approaches to basically provide private or more customizable experiences for the end user. And we're also looking into model tuning, so looking at state-of-the-art models that need to be tested against our existing models using the Ludwig framework, like BERT, XLNet, and other types of transformer models to actually test against the specific models that we've implemented so far. So that is pretty much it. So now we can go into questions.
So you bring the model back in Fusion to and using as a blob store and using part of the pipeline, or you're calling the model as an out other service from the pipeline?
Yeah, so the question was if we bring it into Fusion, the model itself, or we keep it outside of Fusion and call that externally. And we do keep it externally. So there's an actual query stage that calls the actual model service that sits in the same cluster and serves that model for that particular pipeline.
So an array call like any other service.
Yes, but yeah, a specific stage within the actual query line pipeline itself, which is actually available in Fusion 5. Which is available in Fusion 5. Any other questions? All right. Thank you for attending. Also, we have our Twitter signs there, so if you need to ask any additional questions, you could reach us there.